right, how's it going, everybody? It is Tuesday here. We're looking at talking about our second video of the week here, covering our chapter 3 topics in probability. Um, and so we're going to kind of pick up today right where we left off yesterday. Yesterday, I was talking my way through a couple examples, and I decided to leave off the last example for today. It's going to perfectly serve as our introductory example here today to kind of get us rolling here. So, what we were wrapping up with last class, or last video. See, I can't even not say it like we're in person. Is that we were discussing the difference between independent and dependent events. And what we stopped right before we talked about is our difference between overlapping and non-overlapping events, or what are known as mutually exclusive events. Two events are mutually exclusive if they do not share any possible outcomes. That would be the equivalent of non-overlapping. So non-overlapping and mutually exclusive are the same thing here. We're going to kind of allow our last idea from 3.2 to be our first idea here for section 3.3. So what section 3.3 is going to talk to us all about is it's going to talk to us all about our and our or probabilities. In general, the most generic thing that we want to remember here is that the word and is going to indicate to us some sort of multiplication or division between our probabilities, and the word or is going to tell us to perform addition or subtraction between our probabilities. When we discuss these and probabilities, we need to know if the events are independent or not to understand how we perform multiplication or division. When we talk about our or probabilities, we know we're going to do some form of addition subtraction. To know what addition subtraction to do, we're going to need to know if these events are mutually exclusive or not, or overlapping or non-overlapping are other words that are associated with that. In general, we want to realize that there's some kind of keywords that are associated with each of our keywords here. Again, for all the and probabilities, we got to make this determination of independence. For all the or probabilities, we need to make the determination of overlapping status between the two events. So let's look at some examples and see what we mean about all these words here. Generally, the book starts with the and probabilities, but or probabilities I think are easier to understand. So let's do these ones first. The and probabilities have a little bit more notational stuff going on, and a couple, I don't know, a couple more scenarios that can crop up with the and stuff here. So I don't think the and things are too hard, but I do think that the or things are easier. So let's talk about our first like basic scenario here. This is the scenario that I was intending to lay out for our last example from last class. So I'm going to call this scenario 1. And all this is saying is we're playing a game with a full deck of cards. So I'm going to try and keep up my helper document over here. That's going to kind of hold the information of the currently being discussed scenario so that I can scroll away from it. So in general, for a deck of cards, I guess I should say I generally expect you guys to know the basic breakdown of a standard deck of playing cards. It's certainly something that you could Google if you don't know any of this information. But in general, if we have 50, there are 52 cards in a deck. Half of the cards are black and half of the cards are red. The black cards are made up of the two suits, clubs and spades, 13 cards each. The red suits are made up of the red cards are made up of the suits, hearts and diamonds, 13 cards each. Those 13 cards each that belong to each of the four suits are ace through 10. Ace through 10, that's 1 through 10, and that's 10 cards, as well as a jack, a queen, a king. That's 3 more cards to make 13. We generally refer to the jack, the queen, and the king as face cards. In most games, aces count as 1. So whether or not an ace is counted as a face card is sort of dependent on the game. But jack, queen, and king certainly all qualify as what we refer to as face cards here. So let's try and answer these two questions in relation to the scenario that we're looking at right now. So the first question is, what is the probability that we pull a heart or a diamond? And you should notice that certainly the thing of interest here is that the special word is or, that is between the two possible events of interest here. And so I want to make some probability statements for myself that are going to kind of help me figure this guy out. So the first thing I might want to think about is just what is the probability of pulling a heart. And so I could maybe make for myself a statement here. If I want to know what is the probability that I pull a heart from the deck, I'm going to just look over at my scenario information. What I see is that out of all of 52 cards, 13 of them are hearts. Right? So this should be 13 out of 52 cards are hearts. And certainly this represents 1 in 4 suits, where there are 4 equally distributed suits in the deck. So either of those fractions would be appropriate. Alternatively, we can think of what is the probability that we pull a diamond. And again, I see that it is the case that 13 out of the 52 cards in the deck are diamond, which does represent 1 out of the 4 suits that all have the same number of cards here. So if I want to know what is the probability of and I'll start using some slight shorthand here, the heart or pulling a diamond, well, what I know is that there are 13 cards in the deck that are hearts. There are 13 cards in the deck that are diamonds. There aren't any cards that are both hearts or diamonds. And those are separate from each other. And so it seems to me that in this case here, we should be able to compute this as the probability that we pull a heart plus the probability that we pull a diamond. In this case here, I'm going to evaluate this as, call this 13 out of 52 for the hearts, plus 13 out of 52 for the diamonds. And that's going to tell me 26 out of 52 cards are either a heart or a diamond. This certainly reduces down to 1/2, so I would say that either of those would be our good fractional answer right there. I like 26 out of 52 because it does tell me the raw numbers that we're dealing with. That's literally 26 out of 52 cards in the deck are hearts or diamonds, but mathematically it might be nicer to say half of all cards are hearts or diamonds right there. Now, number 2 is going to be a little bit different than number 1 here. We can still talk kind of about the same ideas to set this up for ourselves. Now we're looking at what is the probability that we pull a queen or a spade. So again, I want to think about what is the probability I pull a queen. And the probability of a queen, well, I can see over here, each suit has 1 queen. There are 4 total suits, and therefore there should be 4 total queens out of all 52 cards. Similarly, I can think about what is my probability of pulling a spade. I know that a spade, there are 13 cards in each suit, and spades are one of the suits, so it should be that 13 out of 52 cards represent the spades. And so my question now is this: is it going to be the case that the probability of getting a queen or a spade, is it going to be the case that it's the probability of a queen plus the probability of a spade? I'll put a question mark here to say we're asking the question if these are equal. And here's what I like to think about. I want to literally picture the cards that are in my deck. All right. I want to literally think about the cards that exist in my deck that I'm counting towards my probabilities here. When I talk about what queens are in the deck, I know that there's a queen of hearts, a queen of diamonds, a queen of clubs, and a queen of spades. When I talk about the spades that are in my deck, I know that there's an ace through 10 of spades, and then a jack and a queen and a king of spades. What I'm kind of realizing here is that one of these 4 is the queen of spades, and one of these 13 is also the queen of spades. So what's going to happen here is if we did just add up all the chances of getting a queen and all the chances of getting a spade, you should notice that what's happened is we've accounted for the probability of getting the queen of spades in both of these groupings. But there's only 1 queen of spades in the deck. There's not like a double chance that we're going to get it just because it's our event of interest right here. So here I want to say this is, we do not get this, because events Q and S are not mutually exclusive. I want to show you what I mean in a Venn diagram here. My justification by Venn diagram before we get an answer to this question here. I think it's easy to see this if we draw a nice picture for ourselves. All right, so I want to think about all of my spades and all of my queens here. So if I'm thinking about my spades, I've got my ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got my jack and I've got my king, but I know the queen is actually belonging to both sets. So I'm going to indicate that as the queen of spades. We've also got the queen of hearts the queen of diamonds, and the queen of clubs. All right, those are this is the Venn diagram relating the spades in the deck to the queens of the deck. And so what you should notice is that if we added up all of the representatives of the spades, and if we add up all the representative of the queens, then we've actually added the queen of spades 2 times in our probability counting. And we only really want to count it 1 time. It's only 1 card in the deck. So it looks like if we did, so let's say it like this: all spades plus all queens. What did we get? We got all spades only plus all queens only plus 2 copies of the queen of spades. All right, and that is our problem right there. Oops, let me write the word only correctly. Only want 1 copy. All right, so again, if I add up the spade stuff only, I get the non-overlapping part on the left. If I add up the queen stuff only, I get the parts on the right. But you should notice if we add both circles entirely, we're actually getting 2 copies of the stuff that's in the middle. And I don't want to double count this guy. So since we're getting 2 copies of the stuff in the middle when we add these 2 groups together, I want to go ahead and subtract one of the copies of the stuff that's in the overlap in the middle right here, so that everything is only counted once. So what it seems to me that we should be doing now here is, because the events Q and S are not mutually exclusive, we have that the probability of a queen or a spade, we want to get all of the probability of getting a queen. That gets all of our queen stuff. We want to add all the probability of getting any spade. That's all of our spade stuff. But if we've done that, we've double counted anything that's in the overlap. So we don't want to double count it. We just want to single count it. So let's remove 1 copy of the stuff in the overlap. All the things that are both a queen and a spade, which in this case is just the queen of spades. So I think I can compute this probability now. The probability that we pull a queen is the 4 out of 52 queens in the deck. The probability that we pull a spade is the 13 out of 52 spades in the deck. But this counting has the queen of spades, and this counting has the queen of spades. So we've double counted the queen of spades. So let's remove the 1 copy of the probability of getting the queen of spades from this computation to make sure that we only actually count each card as having one unit of probability in a sense. Here, 1/52nd of a chance of being drawn right there. All right. So again, because our events were not mutually exclusive, because there is overlap between these 2 events, getting a queen and getting a spade, we would double count the probability of the stuff in the overlap by adding these 2 Venn diagram circles together. So therefore, we remove 1 copy of the counting so that we still account for the queen of spades just 1 time here, just like we should. So it looks like in total up top here, 4 and 13 is 17, minus 1 is going to give us 16 out of 52 cards are going to be a queen or a spade, or I guess we could say both. And I don't have any interest in reducing that fraction right there. And again, if you're unconvinced, then you should just list the cards that we're actually talking about here. We have the 13 spades. And we also have the queen of diamonds, the queen of clubs, and the queen of hearts. And I'm not including a queen of spades here because I got the queen of spades in all the spades over there. There's your 16 out of 52 cards that are right there. So what this says to us in general is, I'm going to scroll back up here, when we're doing OR probabilities, we do just want to add up individually the two probabilities. Up here, hearts and diamonds are completely separate. It's not possible to pull a card that is both a heart and a diamond because they are separate suits. Since there are these two events, heart and diamond, were not mutually exclusive, we didn't have to worry about anything getting double counted, and we just straight up added the probabilities. In this scenario, we saw that drawing a queen and drawing a spade are overlapping. They are not mutually exclusive. Sorry, I might have misspoke up here. I'm just going to re-say it again for number one. For number one, these events are mutually exclusive. They are separate from each other. There's no way for both of them to happen at the same time. So therefore, we just did direct addition. Down here, it is possible for both of these events to happen at the same time, drawing the queen of spades. Therefore, it was not appropriate to just directly sum their probabilities because that would have resulted in us double counting the probability of the overlap. So rather than double counting the probability of the overlap, we just wanted only one copy. So we subtracted off one of the two copies that we had, so that only one copy of that card counted right there. And we can see that clearly in this example by literally thinking about the cards that are in the deck that we've got right there. So when we see the word or, that says do addition. However, we still need to determine are the events mutually exclusive or not. If they are not mutually exclusive, if they have something in their overlap, then it matters that we only single count the overlap stuff by subtracting off one of the two countings of it that we've accounted for. So our general rules then for OR probabilities. OR says do addition. Our general formula is right here. The probability of A or B is the probability of A plus the probability of B minus the probability that you're both A and B. You should notice that if our events are mutually exclusive, then this is just zero, right? This probability of A and B is zero, right? This is like the probability of getting a heart and a spade. There is no card that's both a heart and a spade, so that has a probability of zero. So what we can really say is if the events totally are mutually exclusive, if they're completely separate from each other and couldn't ever overlap, then when you see the word or, that just straight up says just do addition between each individual probability, which is really easy. On the other hand, if they are not mutually exclusive, if they are overlapping, if they have some overlap between them, then when you split up over the or word the individual probabilities by addition, this will result in the overlapped stuff getting double counted. And so we remove one counting of it so that everything just is counted once, as it should be. You should also notice that we can use our union and intersection symbols also to notate this. It's actually much more typical to see this written in the second format here with the unions and intersections. It's conveying the exact same idea. We're just given a little bit of notation for this to go along with this rather than just using our words right there. So if you like the union intersection notation, use that. If you like the and the or words, use that. But at the end of the day, your responsibility is to know that the word or says addition and maybe a subtraction, and you have to judge, are the events mutually exclusive or not? And by the way, this is also a sentence, I think, right here that'll help you out with some homework questions right there. Some homework questions will say things like, determine if these events are mutually exclusive. And they'll just give you a bunch of numbers and not like a scenario. Here, the scenario is easy because I can picture a deck of cards. But if we ever need to do some form of computation to determine if events are mutually exclusive, if you can show that the probability of A and B occurring is zero, then it must be that the events are mutually exclusive. That says they can't happen at the same time. If the probability of events, or if the probability of A and B is zero, then A and B could not occur at the same time and therefore are mutually exclusive. So now we are going to talk and probabilities. And again, these aren't really much harder, but there just is a little bit more going on, and a little bit matters more that we pay attention to some notation associated with the and probabilities here. So our next scenario is going to be pretty easy. This one will be the sort of the easy part, the setting up the statement. Then we'll look at some a little bit tougher example that goes with this guy here. So this is kind of some of the stuff that we saw yesterday. I just want to like really emphasize the difference between example one and example two right here. What you should see is that they are both referencing the same scenario, bag of marbles, 5 red, 5 green. I don't even need a third color. That's just adding unnecessary parts to this here. Notice that the only difference between these two sentences is the word with changed to without when I went into example two. So we're just trying to compare these two situations right here. So suppose we pull 3 marbles from the bag with replacement. So that means that when we say we pull 3 marbles from the bag and we want to know what the probability that they're all red, what we're really looking for here is we are really, the probability that they are all red, this should really be like the probability of red on the first and red on the second and red on the third. Now, what I know in this scenario is I can stop and think about what does my one individual scenario look like? What is the probability of pulling a red marble? Well, it looks like it's 5 out of 10, or in this case, we could call it 1/2 right there. So what I want to think to myself is I'm first going to draw a red marble, or first I'm going to draw a marble, and I want to know what the probability that it's red. The very important thing here is because I am putting the marble back in the bag, the probabilities for my second draw are exactly the same as the probabilities for my first draw. The probability for my third draw is exactly the same as my probability for my first and second draw because since we are putting the marble back in the bag every time, it's an identical scenario every single time. So I have a 50-50 chance on the first one, right? I then therefore have also a 50-50 chance for the second one. We're going to multiply these probabilities. Is that a 50-50 chance times a 50-50 chance times a 50-50 chance right here? We have 3, 1, and 2 chances that we would collectively like all 3 to be successes. So there's one way to get a red out of the bag out of the 2 overall ways, red and green, or I should say that there is 5 out of 10 chance that we're successful on the first, and is going to tell us do multiplication. There is a 5 out of 10 chance we're successful on the second, and says do multiplication. There is a 5 out of 10 chance that we're successful on the third. And this one, I think it's way easier to just to think about these as the 1/2 times 1/2 times 1/2. And in that case, we can see that there is a 1 in 8 chance in this scenario that we will pull 3 reds in a row. By the way, since these are just 50-50 chances, you should notice that this is equivalent to things like saying, what is the probability that you have 3 children and all 3 are boys, or all 3 are girls? We're going to get a 1 in 8 chance because there are 3 50-50 chances that are being multiplied together. Half of 50% is 25%, half of 25% is 12.5%, and that's exactly the decimal or percentage associated with 1/8. Now, the important thing that happened here is that because these events were independent, good question. I'm laughing at you. You bring that up there. Every day when I start my lectures, I've always been kind of like quiet in my house, and then all of a sudden I start talking loudly, and my dogs are like, "What the heck is that?" And so I have 2 dogs. One that is tall enough for his head to actually be visible. That is Zinni or Zinfandel. And then the shorter dog that I pet, whose head is short enough that you cannot see it, is Hattie or Manhattan. And so Zinni and Hattie are regularly waiting for me. They spent all summer going on a walk right about now, and they're very miffed that that doesn't happen anymore. So they come and see what's happening with lecture. So I try and bring Zinni's head into the frame right here. So you'll continue to see him. Maybe I got to get like a channel point reward for petting Zinni or something like that in here. So let's make some statements here. With replacement, that's telling me that these events are independent. That means that what happens on one event does not affect what's going to happen on future events. And so what I might say here is that the probability of drawing a red on the first is equal to the probability of drawing a red on the second is equal to the probability of drawing a red on the third. These probabilities never changed, right? It was a 5 in 10 chance every time because we were putting the marbles back in the bag here. When we see example number 2, because we are not putting the marbles back in the bag, what we're going to see is that this information right here is going to change. Now the probabilities are going to change because of the fact that those marbles are no longer located within the bag here. So now what I think I can say is the probability of pulling a red on any draw is different every draw. So let's make some statements about what we do know. The probability of pulling a red on the first one is still the same as it was before, right? There's still 10 marbles in the bag on the first draw, and 5 of them are red. You can call that a 1 out of 2 if I want to. But if I'm going to try and pull my second marble, oops, get my P's and my R's mixed up here. My probability of pulling a red marble as my second draw is different. In this case, it matters what I drew on the first draw. And here I know that I'm hunting for the probability that all of them are red. So I think that I want to rephrase this as, what is the probability that I draw a red on the second draw, given that I drew a red on the first draw? In this case here, that's going to say to me, I no longer have 5 red marbles. I now have 4 red marbles. So it looks like now 4 out of 9 marbles are going to be red. And similarly, my probability of drawing a red on the third is going to be the probability of drawing a red on the third, given that I drew a red on the first and a red on the second. Right? So then I'm thinking, oh, 4 is actually down to 3 now. So this should actually be, get some scrolling here. So this should actually be there are now only 3 marbles that are red that are left out of 8 total marbles. So now I'm thinking to myself here, these are all dependent on what has previously happened. If we had previously drawn a green marble, then it would be that there are 5 out of 9 remaining that are red after the first draw, if the first draw was green. So these probabilities now, this 4 out of 9, this 3 out of 8, these are dependent on the fact that we have previously drawn reds. So here, these are dependent events. When we say that 2 events are dependent, what we really mean is that the outcome of the first event influences the probabilities that are associated with the second event. So the fact that this was a 4 out of 9 was fully dependent on the fact that we drew a red on the first event. If we had drawn a green on the first event, this number would be 5 out of 9 marbles are red that are currently in the bag. So since our probability changed based on the outcome of our first event, these are dependent events, and we need to, in a sense, account for that with some of these given statements right here. So it looks like now the statement that I'm actually trying to say here is probability of red and red and red. I might rephrase. Just want to write this a couple different ways so that we can see how we might notate this. Is going to be probability of red on the first and red on the second and red on the third is the probability of first getting a red on the first one times the probability of getting a red on the second, given that we had a red on the first, times the probability that we get a red on the third, given that we had a red on the first and a red on the second, right? So this is a little bit long form of a way for me to state this statement, but notice that I'm not just saying probability of red 1, probability of red 2, probability of red 3. I don't know what the probability of red 3 is. The probability of red 3 depends on what my previous 2 draws were. I needed to know that my previous 2 draws were red to understand how to compute the probability that I'd get a red on the third. So these are all dependent on knowing the previous information. In the other example, and when we did put the marbles back in the bag, it didn't matter what I drew on the first one at all. I could have drawn red or green, and I was going to just keep on getting 1/2 every time. In the dependent scenario here, we have to know what was it that we, what? Okay, you're going to bring that stuff back there, Microsoft Word? just get rid of all that? Did it move it somewhere? Seriously? Well, that makes me sad. Okay, I guess I'll just write everything again. Ah, yeah. So it could be the case that we get other. So Jazz, I'm going to say. So what you're talking about now. So Jazz's question is, what if we didn't get red? How would we write that? Well, we could say something like, what's the probability that you get a red on the second, given that you had a green on the first? And it could just be a vertical bar with like a G1 maybe right there to indicate that to me. But what I kind of think more broadly is that you're now talking about like, well, what are the other things that can happen and how can we generally notate those? You should notice here that I'm very specifically only exact asking about the scenario of getting a red, then a red, then a red. And so in 1 second, we're going to look at a problem where we're, instead of saying find the probability of this one event, I'm going to say find all possible outcomes and their associated probabilities. And so I think maybe your question is better answered in an upcoming example right here. So I'm going to kind of wait to answer it, but I'm going to show you kind of a more general way to think about these here. So let me just rewrite this here since I'm apparently just deleted that by scrolling. And if we multiply these guys up, 9 times 8 is 72, times 10 is 720. And up on top, 5 times 4 is 20, times 3 is 60. And so that's going to be 6 out of 72. And actually, 6 over 72 is a 1 in 12 chance. So I think here we can reduce this down to saying there's a 1 in 12 chance that we would pull 3 reds in a row out of the bag if we kept them out of the bag, if we did not do replacements here. All right. So what we kind of want to emphasize here then is these general and rules right here. The and rules say let's multiply some stuff together. And what we saw is that our general formula for A and B is that we first want to do event A, right? This says first just do event A. It's the first event that has no impact from anything else. Then we also want event B to happen here, probability of event B, but we need to know that event A previously happened. It's often not possible for me to compute the probability of B unless I know what the first event was. I need to know that we removed a red from the bag, or else I don't know how to compute the probability of getting a second red. I need to know if our first pull was a red or a green. So that's why we include that given information about the first event. You should notice that if our events are, glad I saw that. If our events are independent of one another, then it doesn't matter what you did first, right? So in that case, the probability of what happened second given what happened first is just the probability of what happened second. This is saying I don't need the information about what happened before because that event is independent of my current event. That's only for independence. Our second example there, they were dependent on one another. I needed to know what my first marble drawn was to know the probabilities for the second. So if we end up in a situation, sorry, I'm splitting screens here. If they are independent of each other and unrelated events, then when you compute the probability of A and B, you just straight up multiply their individual probabilities because event A and event B are independent of each other. What happens on one of them does not influence the other in any way, so we just multiply their two probabilities. On the other hand, if they are not independent of one another, if we're drawing marbles from a bag without putting them back, then we are influencing future probabilities based on what our early draws are. So when I compute the probability of first experiencing event A, then experiencing event B, I'm first going to experience event A and just accumulate events probability. Then I'm going to look at the probability of event B. And you should read this as probability. I'm trying to highlight this right here. It's not letting me. I just want to highlight just up to the B right here because I just want to say to you, this is just the probability of event B occurring. It's just that when they are dependent on each other, there's no way for me to compute P of B without me knowing what happened first. What given that event A has already happened, right? So event A is always just representing the thing that already happened first. If they're dependent on one another, we need to know about what happened in step one to understand what's going to happen in step two out there. So again, pretty similar statements right here. We just need to see that if we get the simple case, we just do simple multiplication. If we get the less simple case, then we need to pay a little bit more attention to how to compute our second probability, understanding that the probability of that second event is dependent on what happened in the first. And it turns out we've actually already seen this last class. I referred to this as Bayes' rule. This is the dude that came up with it, Bayes. And you should notice here that if we just multiply P of A, probability of A, over to this left-hand side, then these are the exact same sentences. These are just an algebraic rearrangement of one another. If you multiply both sides by P of A, then we end up at this exact same statement from above right here. So this is one that we used last class right here, and it is equivalent to our multiplication probability rule right here. So we'll use these two guys here in some coming up examples. I'll come back to reference these when we want to like re-refer to this formula here in a second. And so I think now the next example we're going to do is, yeah, here we go. So Jazz, this next scenario here will have sort of a good example of the question that you were asking here. And here's what we're going to do is we're going to draw a tree diagram to kind of look at all possibilities and notate them. So here's my scenario 3. This is me talking about starting my lectures on time because I always go longer than I mean, but I always start a minute or two late because I'm always like, oh shoot, it's time to go. So scenario 3, on any given day, I'll just make up some numbers here. It's 60% chance that I'll start lecture exactly on time. However, I'm more likely to start the second day's lecture on time if I started the first lecture's day on time. The probability that I start my second day's lecture on time is actually 80% if I started the day before it on time. And I do things on a Monday and a Tuesday, so it's really only those 2 days of the week, right? So what is the probability that I start both days on time? Well, I'm going to define some things here. And let's define some events for ourselves. I'm going to define the events M as start Monday on time. And I'm going to define T as the event start Tuesday on time. Now, what we have been told, what was our given information? What we were given is it says on any given day, there is a 60% chance that I will start lecture exactly on time. That tells me the probability of event M occurring is 0.6, and the probability of T occurring is also 0.6. But I'm also given extra information. I'm more likely to start the second day's lecture on time if I started the first day's lecture on time. So what you should be reading out of this however statement is that the second day's probability of on-time start is dependent on the outcome from the previous day. So this however statement here is telling me that the probability that I start the second day on time, Tuesday, given that I started Monday on time, is actually 0.8. Right? So is that our good with our notation right there? And I'm going to encourage you guys to do things like this. Define events and make them letter names so they're easy to work with. Identify the notation that you would use to just even describe the scenario, right? We're just trying to describe the information in the box over here. Give yourself some math notation that actually helps represent that. It's going to make your computations a lot easier here. So this is sort of how I'd like to set things up. Define the events of interest. Establish what you know based on what's been given in the problem. So the question that we're being asked here is, what is the probability that I start both days on time? So let's actually try and answer question A here. I'm going to have to go on down to my next page here. So probability, so I'm going to say here, probability, let's think about how to say this. Let's just say probably I start Monday and Tuesday on time. So that would be probability of M and T. Well, what we just learned, I'm going to scroll up real quick. What we just learned is that when we're doing these and probabilities, I need to take into account, because these events are dependent on one another, that I first want to compute what's the probability of me being on time on Monday, times the probability that I am on time on Tuesday, given that I was on time on Monday. Right? So from our rule, I'm going to compute the probability that I'm on time on Monday times the probability that I'm on time on Tuesday, given that I was on time on Monday. Because for me, those are dependent events right there. They are dependent on one another. The probability that I'm on time on Monday is a 60% chance times the 80% chance that I'm on time on Tuesday, given that I'm on time on Monday. And I can multiply those guys together to get a 0.48 or a 48% chance that I start both of my lectures on time right there. Now, what I think is the more interesting thing to do in this problem is to actually talk about all possible scenarios, right? So this right here is part of a section that we're skipping at the end because we're never going to need to make a tree diagram this semester. On the other hand, I think they're super useful to do to describe everything that might happen. And so I think that we should make this tree diagram here. So before I even make the tree diagram, I'm going to make a separate diagram that I think is a little bit, it might help us get a sense of where we're going. And so I think that what I kind of want to do here is talk about what could happen on any given Monday, Tuesday pairing. It could be the fact that on Monday I am late on Monday and that I'm late on Tuesday. That's possible. I could be late on Monday and on time on Tuesday. I could be on time on Monday and late on Tuesday. And I could be on time for both. What I want to do is talk about what are the probabilities associated with each of these sets of outcomes for me for a given week. So here's how I like to think about our tree diagram for this one here. So I always give myself just sort of like a starting point where nothing has happened yet. What the first thing that needs to happen is Monday. So that's going to be my first branch on the diagram right here. This is going to be the Monday branch. In a second, we'll get a Tuesday branch. What I know on Monday from my problem over here is that I have a 60% chance on any given day of being on time. So my top branches are going to be the on time branches. The bottom branches will be my late branches. I know that, let me get some colors here, that the probability that I am on time is 60%, and the probability that I'm late, therefore, must be 40% or 0.4. And that covers for me everything that I'm doing on Monday. So now I'm arriving at Tuesday, and I'm going to have to make there's going to be another probability event here, right? On Tuesday, I can either then be late or on time. I can either be late again or on time for the first time that week. So again, this is going to be my on time branch. This is going to be my late branch. This is my on time branch. This is my late branch. These then are the 4 possible total final outcomes for my week right here. This is my on time, on time. This is my on time on Monday, late on Tuesday. This is my late on Monday, on time on Tuesday. And this is my late for both. What I still need to do is identify my probabilities in here, right? So my other probabilities that I want to account for here is, I know that the probability that I'm on time on Tuesday is actually 80% if I was on time on Monday. And therefore, it must be only a 20% chance that I am late on the second day, given that I was on time on the first day. On my second one down here, we have no other information suggesting that there's going to be any difference associated with us having been late on this day. So we were told that there is a 60% chance on any given day that I start on time. And since I was not on time, giving us the extra information about the 80% here, this should be another 60% chance of being on time, 40% chance of being late. And so in total now, I can compute my probabilities for all of these events. This should be the 0.6 times 0.8. That's going to be 0.48 or 48%. This should be zero point 0.6 times 0.2. That's going to give me 0.12 for a 12% chance. This guy is going to give me 0.4 times 0.6. That's 0.24. That's 24%. And this guy here is going to give me 0.4 times 0.4. That's 0.16. That's our 16%. And very importantly, as our last computation to do here, notice the good thing about the tree diagram is it does help us add up all of our relevant probabilities here. We've got a 12%, we've got a 24%, and we've got a 16%. Should notice that those make 40%. Should notice that those make 60%. And that says we've accounted for 100% of all of our information here. So tree diagrams can be nice when you don't necessarily have one specific outcome of interest. You just want to generically say, here's my probability scenario. What might happen? This is everything that might happen. I now have a full description of the chance of every combination occurring in my week from this tree diagram of just placing individual probabilities on that branch. And to compute the overall probability that we land on any of the leaves on our tree, we just multiply every consecutive probability that we see on every branch on the way there. So tree diagrams are good. They are good for more general information about a scenario rather than computing one specific quantity. As you can see, we in a sense answered 4 questions here instead of just one. But a lot of cases, it's better to see this because you don't necessarily have one pointed question that you're asking. So tree diagrams can be nice for that. All tree diagrams should ultimately end up representing 100% of all possible cases that could happen out there. So there we go, Jazz. I think that's maybe my slightly better descriptor right there. And also, by the way, we can give some other notation for these. Maybe this is like the other thing I could have said right here is that we can describe these here then as like probability of Monday. And this would be Monday and Tuesday. This would be our probability of Monday and not Tuesday. This would be Tuesday complement because we're late on Tuesday, and so on. So we can also use, we're going to use this complement indicator here in our next example to indicate that we, for example, T complement would be not on time on Tuesday. It's the not probability that's associated with those guys. Man, that I kind of like the idea of that galaxy pen right there, but it's certainly not very readable, is it? I'm going to stick to the red and the black here. Okay, so for scenario 4 here, what am I still drawing? So for scenario 4, let's look at a couple other of the things that again, this is going to be a bit about showing our work right here, and then I think this will probably be, we might look at a 5th example here today, but I think it's one that we sort of already looked at yesterday. So depending on how long this takes us here, maybe we'll do that as well. So scenario 4, we want to take a look at testing positive and negative associated with having a disease. This is something that we're going to talk about a couple times this semester. We should be aware that when we get tested for things that we will experience rates of false positives, false negatives. These are associated with testing errors, which we will come to refer to as type 1 error and type 2 error. And these are really, really, really important things for researchers to consider when we're talking about developing, drugs for things like that. Yeah, no problem, Jess. Because researchers really need to know what the risks are associated with maybe getting an incorrect test result. For example, obviously right now, if you were concerned that you maybe have the coronavirus, if you were to go and get tested and the test comes back negative, even though you are positive, then that means that you might feel more comfortable going out and being in contact with other people because of that negative test, but you're actually positive, so you're probably spreading it around, right? So in a lot of cases, when we're testing to see if a person has a disease, it's generally very, very bad if somebody receives a negative when they are in fact positive. It is therefore often the case that tests will often be more likely to tell you that you're positive than even if you are, because the bigger risk is that you are positive and don't know it. As a good example that I will bring up a little bit again later when we talk about these, when I was in graduate school, this is my like great probability story here. When I was in graduate school, I went to go donate blood one time, the thing that I like very regularly used to do in my life. You can donate every like 52 days or something. And I was like, I would schedule something like 7 weeks out every time or 8 weeks out and donate like super consistently. So in graduate school, it was actually one of my buddies in the math department that arranged a blood drive on campus. I went and did my usual. It was probably my like 30th donation in my life at that point in time. I went and donated blood. And about 4 weeks later, I got a letter in the mail from the Red Cross, and I opened up this packet of mail. It was pretty funny. My current wife, not even my fiance at the time, just my girlfriend that I lived with in Montana. She had just walked in the house, just plopped down the mail next to me as I'm doing my homework, and there's this little like kind of thick envelope I got from the Red Cross. And she, she thought nothing of it. She just threw it on the table and walked right past me. And so I open it up and I pull out this like, it's like a, probably like 8 pages, like tri-folded. And I open it up and I read, and on the first page it says, "We regret to inform you that you have tested positive for HIV." Which I thought was a pretty outrageous first sentence for them to put right there. The very good news is that I know statistics and that I know that just because I received a positive test, it actually still is less than a 50% chance that I was actually positive. But holy cow, that was like super duper scary. And in the letter, they're like, yeah, we only test your blood once. You should certainly follow this up and get a second test to confirm or deny this, blah, blah, blah. But like, man, what I know is that and again, think about this for HIV. There's a huge risk that if you test somebody, they're positive, but the test comes back negative. That's incredibly risky because they think they don't have it, and therefore they're going to participate in behaviors that are associated with not having a concern of that risk, right? And that's really bad because that means that HIV is going to get spread around. On the flip side, the other mistake that we could make is say that a person does not have HIV like me and they do test positive. That's not really that big of a risk. It's not like there's ways that people might get hurt because I had the wrong information. I certainly had a very bad and scary 3 or 4 weeks right there before I could manage to get a follow-up test that confirmed I do not have HIV. But the point is the risk of a false negative is huge. People might go spread the disease. The risk of a false positive is small. One person is going to be scared for a few weeks until they take a second test, right? So we're going to talk a little bit more about false positives, false negatives, and the risks associated with each in our coming chapters up here. But here is exactly a great example of this breast cancer and breast cancer detection right here. Again, a bad scenario would be for somebody to actually have breast cancer, be tested, and get a negative result. That would be really bad. Then they probably would just die because they wouldn't be getting treated for breast cancer. So on the other hand, what would be better is if we designed all of our tests so that even if you don't have breast cancer, getting a positive test isn't going to end your world. It's going to make you terrified for a short period of time until follow-up tests determine that you are in fact negative. But again, the researchers designed their tests for these things to err on the side of caution. We'd rather have too many positives than too many negatives, is a typical thing when we're testing for diseases. So let's talk about this example here. In general, studies show that about 1 in 7 women who live to be 90 will develop breast cancer. That is a pretty generic statistic. Breast cancer is genetic, and so that is not that. There are very few women who truly have a 1 in 7 chance. It sort of is either in your family or it is not. So just so you know, it matters that you know the things that have affected your family in the past for you to know your health risks for the future. Of the women who do develop breast cancer, tests will come back negative still 1 in 50 times. These are the bad ones, right? Even if you do have it, a test will show negative 1 in 50 times. That's 2% of the time. Of all women, about 17 out of 20 tests will come back negative. That's 85% of tests will come back negative. If you were to just randomly select one woman from the entire population, not knowing at all if they have cancer, breast cancer or not, there is just a general 85% probability of receiving a negative. So you should notice that 17 out of 20 is both kind of containing the probability of them having the cancer or not, as well as the probability that the test will indicate correctly whether or not the person does in fact have the breast cancer or not. So before trying to answer any questions, let's first identify the events of interest and define the variables that we've been given. So the events that I've got here, I don't understand why it does different things to me every day. Why can't I just draw? Because that's what I want to do now. I've never seen this screen. Where is this coming from? Draw. Now I have to pick it every time? Okay. So our events of interest here. Well, one event of interest I'm going to call BC is um, a woman has breast cancer. And very importantly, do not confuse this with testing positive for breast cancer. This is actual having of the cancer, regardless of any tests. That's what BC is going to be, breast cancer. The other one that we'll look at here, I'll name the event pause. Our book references the event with a capital letter P, and then they end up indicating probabilities as P of P, and I hate using capital P as an event because capital P means to me the probability of some event, so I don't like those overlapping. So I'm going to call this pause, and this will be a woman tests positive. So based on these things here, I think that another thing that I could do is I'm just going to indicate real quick because tests are, it's so common. There's obviously positive and negative results for a test. And remember, in this case, positive results are really the negative thing. A positive result means you do have breast cancer. A negative result is actually a positive experience. It means you don't have breast cancer, right? So negative, I'm going to, by the way, notate this as pos with a little superscript of the C right there to say this is the complement of testing positive. The opposite of testing positive is testing negative. This should be 1 minus, okay, sorry, I'm not going to say that. That's a computation thing right there. I'm just going to say a woman tests negative. Also, I should say, notice that we're only discussing women here. Men absolutely can get breast cancer, but I am pretty sure the tests that they do to detect it are not the same. Because if you are doing some type of blood test, it usually has to do with detecting like hormone levels in your body. And those are not going to match for men and women. So these tests are not likely to either be the same, or even if they are the same, I doubt they have the same error rates for across men and women because they're most likely detecting based on a hormone, and those are going to differ by gender. So it's important here that this is only referencing women's information. And I've got to say, I guarantee that there has been a absolute buttload of research that's been done on breast cancer for women, and very little research, comparatively speaking, done on breast cancer for men since it has such a lower incidence. So the other things, so we've identified our events of interest. Let's also identify the information that was given to us in the problem right here. So those are events. Now let's identify our probabilities, our probs over here. What were the probabilities that this problem just identified for us? Well, it looks like the probability that any woman gets breast cancer, and I should say here by age 90, probability of breast cancer is going to be 1 in 7. Our probability of having a, let's see, what's our next sentence say? I'm just trying to go sentence by sentence and extract this information. Of the women who do develop breast cancer, the probability of a positive test is 1 in 50, given that you have cancer. So probability of positive, given that you do have breast cancer, that's a given statement right there, is going to be, oh, sorry. This is our, the women who do develop, tell us to come back negative, sorry. That should be negative right there. Probability of negative, given that you do have breast cancer, is a 1 in 50 event, 1 in 50 probability. And finally, of all women, 17 out of 20 tests come back negative. So the probability of just negative with no known information is just 17 out of 20. And by the way, I do feel like this is one of those things where like, I'm probably going to ask you to do a question like this on our first test, where I really won't even be doing any computations, just like state in terms of our typical probability notation the information that's in this paragraph. Convert a paragraph into good math notation. That's all we've done right here. And it's important understanding that that middle statement was a given statement, a dependency statement, that whether or not we test positive or negative should be dependent on whether or not we have breast cancer. Otherwise, this is a terrible test, right? These are certainly dependent events, so making some of these given statements do matter here. So let's answer a couple probability questions based on these things right here. We need to come back up and reference these a little bit, I think. So what is the probability the woman does not develop breast cancer by age 90? So what is the probability, I would say, as BC complement? What's the probability we do not experience that event? Well, one of the things we talked about last class is that the probability that you do develop cancer by age 90, breast cancer by age 90, plus the probability that you do not develop breast cancer by age 90 has to be 100% because you either do or you don't. So what we can always do here is say, well, the probability that we don't is always the part of the probability that's remaining left over out of the original 100%. So this is going to be saying there's a 100% chance total that we're going to either have breast cancer or not by age 90. If we subtract off the probability that we do, then that should leave us with the probability that we don't. And so here, this should be 1 minus the probability that we get breast cancer by age 90 is 1 in 7. And so I could think of this as 7 out of 7 minus 1 out of 7 to give us a 6 out of 7 chance that you do not develop breast cancer by age 90. This is a complementary probability. And complementary probabilities, we can always, in a sense, flip them and talk about the forwards probability rather than the backwards probability by introducing that 1 minus to say it's the other parts out of 100%. So question 2, what is the probability that a woman has breast cancer and tests negative? So here I could write this as, what is the probability that woman has breast cancer and tests negative? Well, as we've seen from our computations here, I know that my test results are dependent on whether or not I have cancer. I'm way more likely to test positive if I do have breast cancer than if I don't. Since these are dependent events, it matters that we compute our probability according to the probability rule that we established before, which is that first we just want to know what's the probability of having breast cancer. Then after that, we want to know what the probability of having a negative test, given that we do have breast cancer. I know the probability of having breast cancer by age 90 is 1 in 7. I know the probability that we'll get a negative test, given that we have breast cancer. We've got that one right there. It's a 1 in 50. And so we get a 1 in 50 here. And so that's going to tell me that we have a 1 in 350 chance of having breast cancer, but testing negative, which is obviously incredibly unfortunate. And I'll say breast cancer goes super quick. My mother actually died of breast cancer about 6 months ago. And it was only about 2.5 months between detection and her passing. So it really matters. It really matters that we don't end up in these situations. So one of the things that researchers are always working on is making sure that this number right here, very specifically, is as small as we can ever make it, because the biggest risk for people is that they have a disease, but that when they get tested, it shows negative. We have a lot of trust in modern medicine now. If a doctor looks you in the eye and says you don't have breast cancer, then you're probably going to live your life based on the fact that you don't. If a doctor tells you you don't have HIV, you're going to live your life as if you don't. So it matters that we get good information out there for these things. So this is a really, really, really highly studied number. A lot of efforts in cancer research is focusing on making this value as small as possible. People are going to get cancer. We would like to know for sure when people do, so that we can treat it as effectively as possible here. So number 3, what is the probability that a woman has breast cancer or tests negative? So we can say, what is the probability that we have breast cancer or that we test negative? Now we're talking about our probabilities associated with these guys here. Since we are looking at an or statement here, we want to make sure that we extract some of our sort of overlapping information that we might end up having right here. I guess I wrote test negative right there. This should just be probability of BC or negative right here. And so let's ask the question here. Um, Wait a minute, do I mean to change that? Okay. So what we should notice is that since this is an or probability, what we need to ask ourselves is it possible for these two events to overlap? And it is. What we know is that you can both have breast cancer and test negative. Since these both could be occurring for the same person, we need to account for that overlap. So what I'm going to say here is we should have the probability of breast cancer plus the probability of being negative minus the probability of BC and negative. I'll end that right there. I know I'm falling off the screen right there. And so we know most of these probabilities right here, right? The probability of breast cancer, that's 1 in 7. The probability that we will get a negative test, that was given to us. 17 out of 20 tests come back negative across all women. And we just computed the probability that you have it and test negative, right? BC and negative. That was something that we just worked out in the previous problem. That's that 1 out of 350 right there. So minus 1 out of 350. This looks like it's going to be a bit of a bummer of a fraction right here, but that's what we have all got our calculators for. 1 divided by 7 plus 17 divided by 20 minus 1 divided by 350. And I'm going to have it convert this thing into a fraction for me. Wow, really? Oh my gosh, that works out incredibly nice right there. That worked out to exactly 99 out of 100, which is 0.99, or 99% for this guy right here. Right? So notice sometimes it might be that you need to break this guy down. Notice that I could have totally asked you question 3 before question 2 where you already knew that information. For question 3, you should have known to write this probability statement. You should have realized that you didn't know this quantity, but that you can go and work through what that quantity must be. So this was based on both dependence and overlapping events. Both kind of come up at the same time here in number 3. Finally, let's do number 4 here, and I think we'll go ahead and call it a day here. So what is the probability that a woman has breast cancer and test positive? So since this is an and probability, I need to ask myself, are these independent or are these dependent? Our test results are definitely dependent on whether or not we have breast cancer. We have a much higher chance of testing positive if we do have breast cancer than if we don't have breast cancer. So these are dependent. So I know that I'm going to write this as the probability of breast cancer times the probability of a positive test given that we have breast cancer. So we're going to need to decide what this statement is going to be right here. I know the probability of breast cancer in general is going to be that 1 in 7. What I don't know is this probability of positive given breast cancer. If I scroll back up and look up here, I have a probability of negative given breast cancer. So what we should see here is that negative is the complement of positive. Complementary probabilities can always be handled with the 1 minus swap. And I know the probability of negative given breast cancer here is 1 out of 50. So it should be the case then, I'll add this here as a second color, that the probability of positive given breast cancer should be 1 minus 1 over 50. And I'll write this as the complement of negative. The complement of negative is positive, right? It's the other part. And that should be 1 minus 1 over 50, which, doing a little fraction math, 50 over 50 minus 1 over 50. It looks like it should be 49 out of 50 people do get a positive test if they do have breast cancer there. So what I'm going to write this guy as down here then is using our information from above, I can write this guy as uh, let's see here. This is probability of, and I'm going to write, this is sort of longhand. I would definitely not expect you guys to write all this stuff out. I'm just writing this to make absolutely sure we see exactly why I'm doing what I'm doing here. So positive is the complement of negative. To compute a complementary probability, we can just look at 1 minus the probability of not the complement of negative right there. This is going to be our 1/7 times our 1 minus 1/50th. That will be 1/7 times 49/50ths. And you should notice here we can do actually a little bit of nice fraction cancellation right there and just get 7 and 49 cancel, leaves us with 7. And so a 7 out of 50 chance. So probably the woman has breast cancer and tests positive. So this is saying if you're to draw a random woman and if determine if they have breast cancer and a positive test, 7 out of 50 women will have breast cancer with a positive test by the age of 90. So that's 7 out of 59. That's slightly fewer than 7 out of, or sorry, 7 out of 50. That's slightly fewer than 7 out of 49. 7 out of 49 is the 1 in 7 women that will get breast cancer because not quite all of them will also get a positive test. So this is a number that's ever so slightly smaller. I should just say it here, 7 out of 50 is a little bit smaller than 7 out of 49, which is the 1 in 7 women that do have breast cancer. So slightly fewer, the ones that are going to get an actual, because some are going to get a negative test, unfortunately. So it's not all of the women that have breast cancer are going to get a positive test. Slightly fewer of them are the ones that will both get it and have a positive test for it. So 7 out of 50 women that live to the age of 90 will get breast cancer and experience a positive test when they get it there. So I hope kind of the thing that you guys are seeing from this video is that one of the really important parts about this section here is get good with your probability notation, indicating these things with the ands and the ors, breaking down the ors according to our or rules, breaking down the ands according to our and rules. It really matters that you are good with the notation to be able to use these rules. The good news is that our rules amount to only addition, subtraction, and multiplication between quantities. The bad news is that it's never obvious which one you should do unless you're using your notation properly right here. Again, I think this is a little bit overkill for showing my work on this one right here. With these couple extra lines, I could say at least one of these lines could be not written right here. But again, understanding that this positive test given breast cancer, given that we have it, is the complement of a negative test given that we have breast cancer, is what's helping us to compute this complementary probability, the 1 minus 1 over 50 instead of the 1 over 50. If you have breast cancer, you either get a positive test or not. That should represent all 100%. That 100% is represented as the number 1 that we see sitting right there. So the only other things I was going to look at today was just another example of a contingency table, but we did one of those yesterday. I didn't have many other questions of interest to ask that were much different than the ones from yesterday. So maybe I'll just say, if you have contingency table questions in the homework, you should certainly just send me a message in My Open Math, and I would be very happy to talk you through those. Maybe as my final statement for the day, I'll say, I noticed a couple people were having trouble with problem number 16 in week 3's My Open Math homework, which dealt with the number of days of service from Supreme Court Chief Justices. I gave an explanation as to why the people that are getting that a little stuck on that one, there's for a very good reason with what the computation is that we're doing in Excel. There's something I told you to do in one of last week's videos most of the time, and it turns out that that homework problem is a good example of when not to do the thing that I said to do. So if you look in Canvas, I made a little page that's like, help with your homework for this week. In general, if any people are asking me questions where it's like, oh, I should have explained that differently, or oh, that's something probably everybody needs to hear, I'll add a little page in Canvas so that everybody can kind of hear my answers to those questions. So just be aware that those things might pop up in Canvas if people have questions, or won't if people don't have generic questions like that. this week there was one of those. So if you're looking for that little bit of help on number 16 on the week 3 homework, then I wrote a little blurb to kind of get you through the Excel computation in there for that one. And again, if you guys have other generic questions about some of those homework problems, I'll always kind of post more general things that I think everybody might want to see in Canvas so that you guys can see the reference to those things. So hit me up with any other questions that you guys have. Otherwise, this will kind of wrap up the core stuff of what we're looking at with all of our probability computations. I think our biggest things from this chapter are you need to be able to deal with fractions and percents. You need to be able to understand and or probabilities. You need to understand that and means do multiplication, and that we need to understand if events are independent or not. We need to understand that our or situation tells us to do addition, and we need to know if our events are mutually exclusive or not. And we should be able to extract all of these types of pieces of information from contingency tables by looking at the marginal distributions, our totals for the rows, our totals for the columns, and using those to help us compute some values of interest like we did at the end of yesterday's video. So again, hit me up if you guys have any questions about any of the things that we got here in week 4. Next week, we're going to start looking at some of our probability distributions, our uniform distribution, our normal distribution, start computing some probabilities of interest very specifically from the probability distributions that we'll be working with for the rest of the semester. Also next week, we're going to take our first test at the end of the week. And so I am going to send out information to you guys about what will be on that closer to the end of the week this week so that we all know what to expect. So plan on doing something that is more like a test Thursday and Friday of next week, just to make sure that everybody's got time to actually be ready for that. So end of next week, you'll have a couple days to do a test, and we'll get more information about that at the end of this week here. That wraps it up for me today. I will see you guys in the email, in the My Open Math questions, in office hours, at Monday's video lecture, all that good stuff. Contact me with questions. Have a good one, everybody.